Good afternoon, everyone. It's truly a pleasure to once again have the opportunity to participate in this conference. We would like to express our sincere appreciation to the Symposium Committee and to the University of Bahrain for organizing this event. So my name is Sarah Boudouh. I'm an associate professor at University of Lagos and a researcher at the LIM lab in Algeria. So in this presentation, we will provide a brief overview of our work titled Tuberculosis Classification from Chest X-rays using hybrid CNN transformer architecture, leveraging long short-term memory feature selection. So in this presentation, we'll start firstly with an introduction where we'll highlight as well the gap, and then we'll move forward to our proposed approach, highlighting all the steps in the framework. Then we'll move after that to the results and their discussion. And finally, we will have a conclusion. So tuberculosis, or TB, continues to be one of the leading causes of death from infectious diseases globally. So chest X-ray is widely used as a primary screening method for TB because it's both cost-effective and easily accessible. However, interpreting chest X-rays accurately requires skilled radiologists, and in many regions their availability is limited, which delays the diagnosis and the treatment process. In recent years, now artificial intelligence and more specifically deep learning have shown great promise in addressing these challenges. By automating the analysis of chest X-rays, AI systems or AI-based systems can assist radiologists to speed up the screening process and to improve the diagnostic consistency, especially in settings with limited medical expertise and limited event data. So, despite recent progress or recent studies, current TB detection models still face key issues. Many of the studies, for example, when they use transfer learning, they activate all the network layers, or they customize their own architecture by initializing the weights randomly, or when they use transfer learning, they activate all the layers, or they freeze them all, and that could introduce some noise from shallow features, and most lack proper feature selection. They also fail to combine global context with local details, which are both vital in medical imaging. So to address this, we propose a hybrid framework that merges the vision transformers for global understanding with the selectivity activated exception network for localized features. And after that, we introduced a long short-term memory layer just to refine these features by filtering redundancy and improving both accuracy and efficiency. So, moving to the proposed approach, and before starting, we will start with the dataset or the used dataset. So instead of relying on just one single dataset, we merged two publicly available datasets to create a more balanced and representative collection. So the first one is called the Tuberculosis TB Chest X-ray dataset, was developed through collaboration between Qatar University and the University of Dahak and Malaysia institutions. So the dataset contains 3,500 normal and 700 TB chest X-ray images. The second one, meanwhile, which is tuberculosis chest X-ray images, includes 2,494 TB cases and 514 normal images, collected from the local hospitals in Pakistan. All images were represented or were pre-processed and resized to a uniform resolution to ensure consistency and facilitates the effective analysis. So by merging the two datasets from the two sources, we obtained a total of 7,208 chest X-ray consisting of 3,194 TB and 4,014 normal samples. We then split these combined dataset into 80% for training and 20% for testing. Now, moving forward to the proposed framework, it is structured into three main phases. First one is the feature extraction, then we have feature fusion and selection, and then finally we have the classification, so where the classes are normal and TB or tuberculosis. So in the first phase, which is feature extraction, we use two complementary methods or models: vision transformers and exception as a CNN, as a convolutional neural network. So the vision transformer capture global dependencies across image patches using multi-head attention, which is composed of just multiple self-attentions, which helps in identifying subtle structures often seen in medical images. Meanwhile, exception, which is a pre-trained model, now which we partially froze to retain its pre-trained knowledge from ImageNet, focuses on localized hierarchical details. We also applied selective activation to only certain exception layers, specifically blocks from 11 to 14, which are in the exit flow of the model. So the flow focuses on extracting high-level task-specific features for classification. Hence, these deeper layers tend to hold more abstract, class-specific information while filtering out noise. This choice helped us to reduce computational load and improve accuracy at the same time. Now, in the second phase, we fused the vision transformer with the exception features by concatenation or by a concatenation layer. Since this creates a very high dimensional space, we passed the fused vector through a long short-term memory network, as you can see. Now, the long short-term memory acts as a feature selector, so it's going to select some of the existing, which are too much feature, including the feature maps from the exception and the features extracted from the vision transformer. So the LSTM here acts as a feature selector, learning temporal dependencies and filtering redundant information, which improves the discriminative power of the representation. And finally, in the third phase, which is a classification phase, the refined features are passed through fully connected layers with dropout regularization and the sigmoid output neuron, just with one neuron, classifies each chest X-ray image as either tuberculosis or normal. Now, overall, this hybrid architecture effectively combines global and local cues, leveraging both attention-based and convolutional learning for more robust tuberculosis detection. Now, moving to the obtained results, and before starting, we should emphasize that we implemented the model using TensorFlow 210 and trained it on an NVIDIA GTX 1660 Super GPU. Each configuration was trained for 50 epochs with a learning rate of 10 to the minus 4 using an Adam optimizer. We evaluated several trials to identify the optimal exception configuration because we didn't decide from the beginning that we are going to use only the exit flow. So we decided after the experiments that the exit flow, specifically layer from 12 to 14, were actually the ones that needs to be activated or trainable, and the others should be freezed. Of course, as shown in the plots, both of the training was monitored on both accuracy and loss, and observed a steady convergence for the best performance model, which combines the vision transformer encoder, the LSTM selector, and the exception blocks from 12 to 14. Now, for the evaluation, we focused on accuracy, recall, and precision, given their importance in medical diagnosis. And here recall is also known in the medical field as sensitivity, to minimize missed tuberculosis cases, because we can see the unbalanced two data sets that we have gathered. By merging them we reach a balanced data set, but still the tuberculosis images were less than the normal images. Now, the best configuration was the one combining exception blocks 12 to 14, the vision transformer encoder, and the long short-term memory layer, achieved 99.93% accuracy. Moving forward, when the LSTM was removed, performance dropped to about 98.3%. And of course, when we moved it as well as the time, there were a time cost as well. Its crucial role, and we can see that its crucial role in feature selection. Meanwhile, activating all the exception layers, when we activated all the layers to be trainable, led to a major decline due to the noise and overfitting, while removing the VIT, or the vision transformer encoder, reduces accuracy into generally the one before. So it reduced it to 55%, highlighting how global and local features complement each other. Meanwhile, removing the CNN, and relying only on the encoder and the long short-term memory reduced also the accuracy to 87%, highlighting how global and local features complement each other. Now, unlike previous studies that rely solely on conventional convolutional neural networks, so the traditional CNNs, or the traditional way of transfer learning, which is just freezing all the layers or unfreezing all the layers, or perform full feature extraction without selection. So we just do the feature extraction, we extracted feature maps, then use them for the classification without any selection. Our method selectively activates only the deeper exception blocks to capture high-level tasks, because the other tasks are actually general for all the data modalities. Based, of course, LSTM-based features filtering mechanism also the whole hybrid design achieves significantly higher accuracy and recall than existing approaches. Overall, these results confirm that selective CNN activation with transformers, specifically here we are talking about encoders, and long short-term memories based filtering together yields a high efficient and accurate tuberculosis detection model. So to sum up, in this study, we introduced a hybrid model that merges the strength of exception as a pre-trained model, vision transformers, and here we are talking about the encoder, and long short-term memories to classify tuberculosis for chest X-rays. By selectively activating deeper exception layers, and here we are talking about exception, and applying long short-term memory-based feature selection, the model effectively reduced redundant information and achieved excellent performance, reaching 99% accuracy. Looking ahead, of course, we plan to integrate attention-based feature selection, so we are not going to rely only on recurrent neural networks, which are the LSTM here in this case. So we are going to integrate maybe also attention-based feature selection and evaluate the framework on larger and more diverse clinical data sets to ensure broader applicability. And here, of course, not just only the feature selection, but also for the feature maps extraction, we can rely on other pre-trained models except the exceptions. So thank you again for your attention, and thank you for the opportunity to present our work. We are glad to be here again, and I'm happy to answer any of your questions.